All right, section 5.3 is about mass and weight. We probably should have had this section a few sections ago, but here it is, so here we are. Mass and weight are not the same thing, but they are related, as we have said already. Mass, the standard unit, is kilograms for us. Mass is an intrinsic property of an object, meaning if you have an object, it will have mass. It has the same value no matter where the object is. Regardless of what forces are acting on it, it always has that mass. It could be on the surface of the earth at sea level. It could be on the surface of the earth at the top of Mount Everest. It can be floating around in space. It will always have that same mass. Weight is a force. So specifically the gravitational force exerted on an object by a planet or the moon or something, okay? Weight is a vector. It is not a scalar. And so therefore it has a magnitude and a direction, and the direction of the vector is always straight down toward the center of the planet or moon or whatever it is that the object is on. Weight is measured in newtons, and weight can change depending on the size of the object or the distance away from the center of the object that you are. So, mass is always the mass, no matter what. Weight is a force, and the weight can change depending on where the object is on the planet, or if it moves to a different planet, for example, the weight can change. But the mass does not change unless you remove some of the material that the object is composed of. So those are distinctions that are very important you have to understand. So at the bottom we have an object in free fall, has only one force acting on it, and that is the weight. It's the downward pull of gravity. So therefore the acceleration is vertical, and I've been trying to make sure that we have this distinction here. Acceleration in the y direction is negative g, where g is the free fall acceleration, and free fall acceleration is actually 9.8, not negative 9.8 meters per second squared. So if we define our positive y direction as up, then acceleration being down is negative. G is positive, so we have negative g because acceleration is down, which opposes the upward direction.
Of course.
So we have the sum of the forces in the y direction then would be negative w, because w would be a vector pointing down. In other words, negative mass times gravity, because gravity was pointing down, which is resisting the upward direction, which is positive. Okay? So hopefully that is making sense. We got to keep those things straight so that we get our signs right, so that we can solve our problems and come up with the correct sign on our answer, and not get a negative sign when we should have a positive sign, or vice versa. Okay, so weight is equal to mg. That is our big deal. So every time we have a problem where we have an object and we have to assign a weight vector to it, weight is actually mg, and we can start off in the problem with mg, or we can start off in the problem with w for weight. So note that although we're talking about an object in free fall when we derive the relationship between mass and weight, the weight of an object is independent of the state of the motion. So the object can be at rest on a table, can be sliding horizontally, moving any way it wants to be moving. The weight is independent of the state of motion. So because the object's weight depends on gravity and the value of g varies from planet to planet, weight is not fixed, as I already said. It is not a constant property of the object. Mass is, weight is not. Your weight on the Earth, on the moon, on Jupiter would be different in all three cases. Also, if you're floating around in space. Even though your mass does not change, your weight does. Your mass would be the same always. Your weight is not the same always.
How come on a scale you keep
Yeah, there you go. Good question. Why don't we just use kilograms? Because we are Americans, that's the answer. So here are some helpful relationships between mass, weight, and force. Conversions between force units, 1 pound is 4.45 newtons. Now, this is kind of an important one because we now realize that pounds and kilograms are not the same thing. Like, we cannot go back and forth between pounds and kilograms if we're talking about weight, because pounds are not the same thing as kilograms when we're talking about weight. Kilograms is a mass, pounds are a weight, newtons are a weight. So pounds go to newtons, and then newtons can be turned into pounds. We do have a conversion from kilograms to pounds, like 2.2 pounds per kilogram, but those are talking about two different things. So that's kind of a strange thing if you think about it. We're talking about a correspondence between mass and weight here, assuming gravity is 9.8 meters per second. We can convert a kilogram to 2.2 pounds if we are talking about gravity being 9.8 meters per second squared. There is some multiplication that's going on behind the scenes in order to make that conversion occur, okay? So when somebody talks about, well, 1 kilogram is 2.2 pounds, you have to remember that gravity was included in that conversion. Also, 1 pound converts to 0.454 kilograms, or 454 grams. Again, you have to remember that there was a multiplication of gravity that was included in that conversion. It is not a direct relationship. Up here, these guys are direct relationships. 1 pound is 4.45 newtons, and 1 newton is 0.225 pounds, because those are force units. They're weights. So you can use this conversion here. You just have to understand that that is not a direct relationship. Okay, so now what are the weights in newtons and the mass in kilograms of a 90-pound gymnast, a 150-pound professor, and a 240-pound football player? So we're trying to find the weight in newtons and the mass in kilograms of these things that we are familiar with in pounds. So the easiest way to do this probably is just to make a table, and then we're going to do the conversions on our calculator. So we need the gymnast, the professor, and the football player. And I'm just making a quick table here. We can do weight and mass. There we go. So how am I going to convert the 90 pounds to newtons? Yeah. Okay.
The football player is 1,068.
1,068. Okay, now we got to think about significant figures. For the football player, it's 2.
So that's just
The gymnast has got 1.
1,000. Yeah. Yes.
1,100?
The gymnast is 400.5, so it's 400.
400?
The professor is 50,000.
So what are you going to say for the professor?
670.
670? Okay, good. Now we got to come up with the mass. How are we going to get that?
Multiply with
Multiply by 9.8?
No, multiply by 0.454.
Oh, yeah.
Oh, yeah.
So continuous is 40.86, you get 40, you get
40.8, is that what you said?
40.86,
With one significant figure, so 40? Okay.
And that's, what is it?
Mm-hmm.
The bubble player is 108.96.
So that will be what?
108. No, 109.
Nope.
And
110.
The best rate is 68.1, so you get to,
67.
68.
Dang, I was so close. I was trying to say off the zero.
it's 68.1.
Yeah, 68.1 will be 68.
No,
Okay.
it could be two from 400 to 40, pick up a zero. 1,100, pick up a zero and move down.
It kind of does seem like that, yeah.
It said 1,100.
1,100 is perfect.
Yes, I take 100.
All right, the next thing we're going to talk about is something called apparent weight. This is something that is felt. Gravity is not a force that you can feel, but the sensation of weight due to contact forces that are supporting you is something that you can feel.
Oh, it's like when you step on a nail and it hurts because you weight.
Well, that's pain. That's different. Okay, so the sensation of weight due to contact forces supporting you. So the normal force exerted on you by the chair you're sitting in, the floor pushing against your feet, stuff like that. If you're hanging from a rope, the friction force between the rope and your hands. Okay, those are the sensation of weight. That's what you feel, okay? Define apparent weight. So W sub APP is apparent weight as the magnitude of the supporting contact forces that you feel. So we have our mass, that's not changing. We have the weight that we are due to gravity, but then we also have apparent weight, okay? That's what we feel. Now, if we are in equilibrium, your weight and apparent weight are basically the same. So as we just sit here, we have contact forces from the chair pushing back on us. We have a little bit of contact force if your feet are on the floor, a little bit of contact force from the table, if your elbows are resting on the table, stuff like that, okay? So if we start to undergo an acceleration, though, in some direction, maybe up or down or side to side, then this is not necessarily the case anymore. We might have an apparent weight that has changed our actual feeling of our normal equilibrium weight. All right, so the apparent weight is something different than our actual weight. Okay, just for example, when an elevator begins to rise, hopefully you've all ridden in an elevator before, right? How do you feel when the elevator begins to rise?
That you're gonna fall and hit the floor.
Yeah, you feel like a little heavier, right? Like it kind of like gets sucked down a little bit. And then once the elevator is at its normal operating speed, like you just start, as you're rising at a normal rate, then it sort of balances out and then you feel normal again, right? When the elevator, now you're rising and the elevator comes to a stop, how do you feel? I don't know what that means.
You feel like you're gonna like fly away.
Yeah, you kind of feel like lighter than normal, like you're kind of floating up, right? And the same thing is true if you're in a car. If you're in a car and you go over a bump, like kind of a quick bump,
Oh, yeah, you like get that.
you get a little floaty feeling in your stomach,
Like
right?
airplane turbulence.
Or if you go kind of in a dip real quick and your car kind of bottoms out, you get that same kind of sinking feeling in your stomach, okay? Those are both weight apparent situations. You feel suddenly lighter than normal, and suddenly feel heavier than normal, okay? So that's the kind of thing that we're talking about here. And you want to keep those in mind as we kind of go through these problems. Okay, so looking at a free body diagram of an elevator, the man feels heavier than normal in the picture, while the elevator is accelerating upward. So right at the beginning, when the elevator first starts to go, you're going to feel a little bit heavier than normal. Because of the acceleration upward, we have the man's normal weight, okay, so we have the weight down, but then we have an acceleration upward, which means we must have an F net up. So therefore, the normal force up must be greater than the weight down, okay? If you look at the free body diagram, hopefully that makes sense. If we're going to accelerate upward, the F net must be up, which means the normal force must be longer than the weight down, okay?
And then if you're staying at a constant speed, so let's say the elevator hit a constant speed going up towards, then you still have that feeling.
Oh, sure. Once the elevator hits a constant speed, then this acceleration vector is gone, the F net is gone, and the normal force regains equilibrium with the weight, and you don't have that feeling anymore, right? Okay, but that's not the case when the elevator first takes off. So this is the situation when the elevator first takes off. We have an acceleration up, there's an F net up, which means the only forces acting on this thing are the weight down and the normal force up, which means that the normal force must be greater than the weight. Everybody agree with that?
Yes.
Okay. So now, if that's the case, then if I do a sum of the forces in the y direction, I have the normal force positive, I'll have a weight in the y direction, which will be negative, right? So here's my n minus w situation, and I have an acceleration in the y direction, so this is the mathematical look at what we're talking about here, okay? Now, so if I just look at this part right here, and I solve for the normal force, what I have is my weight plus some new thing sitting here, okay? So the normal force is the weight plus something else. And that's why my weight apparent is this situation right here. My weight apparent is this normal weight that I have plus this new additional mass times acceleration in the y direction, okay? Because I'm not moving off of the elevator floor, so that's this weight apparent that is balancing me out with the normal force that's sitting right here. That is the only explanation that is possible for me to not move off of the elevator floor, because otherwise I would be moving off the elevator floor.
So assuming this free body diagram is going off the person and not just the elevator, if you're going off the elevator, what's
Right.
that?
No, this is the person. This is the free body diagram for the man in the elevator. Okay? So this is because we must be in balance. So there must be an additional little bit of weight down so that this man is not floating off of the elevator floor. Okay? To keep him on the floor. Now, physically, how do we feel when this happens? We feel heavier, right? We feel heavier than normal. Well, this is our normal weight right here. How do we feel heavier? With this extra little bit right here. So mathematically, that MAY right there explains why we feel a little bit heavier than normal. What?
What is the extra little bit?
It's the MAY that's sitting right there in the equation.
Oh,
All right, so for the case shown, the elevator is accelerating upward, so the acceleration in the y direction is positive. This means the apparent weight is greater than the man's weight, so he feels heavier than normal. If the elevator had a downward acceleration instead, then the AY would be negative A, and the weight apparent would look like this instead. W minus mass times acceleration in the y direction. So then the apparent weight would be less than the man's weight, so it feels lighter than normal. So that explains why when the elevator comes to a stop, if you're going up, you have a lighter than normal feeling, or if you are in the elevator and the elevator starts to go down in the first place, you have acceleration in the negative y direction, which gives you this negative MA right here, and you feel lighter than normal also. Okay? So mathematically speaking, this explains why both of those are true. Physically, you already knew that because you've ridden an elevator before. So when we have weight apparent situations, you have to think about, like physically, how do I feel? Okay, that's my weight apparent, then I'll feel lighter than normal. I'll feel heavier than normal. So this is how we come about those mathematically.
so if there's
All right, Anjay's mass is 70 kilograms. He's standing on a scale in an elevator that is moving at 5 meters per second. As the elevator slows to a stop, the scale reads 750 newtons. before it stopped, was the elevator moving up or down? How long did it take for the elevator to come to rest? What do we do?
Why are we in kilograms and newtons?
Because one's a mass and one's a weight.
One's a mass, one's a weight. That's right. What do we do? I can't really draw a picture because I don't know if the elevator's moving up or down.
Alright, so we're going down.
What do we know?
Mass equals 70 kilograms.
Okay, so what should I do with that mass?
Change it into weight.
Turn it into a weight. So we have the weight equals mass times gravity. We know the mass is 70 kilograms. And we know gravity is 9.8 meters per second squared. So Anjay's weight is what?
686.
All right, 686 newtons. Okay, so now what can we do with this information? So if he's standing on the scale and the elevator is moving at a constant speed, it's going to read 686 newtons.
He's starting it. He's going up. He's starting and he's going up. So he's feeling heavier than normal because he's weighing more than.
The elevator is slowing to a stop. Now it reads 750 newtons. So what happened? He's going to feel heavier, right? So we're slowing to a stop and we're feeling heavier. Are we going to be going up and slowing to a stop, or are we going to be going down and slowing to a stop? We're going to be going down and slowing to a stop. Okay, physically we know that because we've ridden an elevator before and we know slowing to a stop, going down we're going to feel heavier. So we know it's going down. Okay, now that we know that, we can probably come up with an answer to this problem. What do we need to do next?
No, make a, now we can make a picture.
A picture.
You know, the other is going down, so it's just understand what we have.
I don't think we need a picture here.
Nice job, Cole.
The question is asking for how long does the elevator take to come to rest. What are we looking for here? Yeah, we need a delta t. So in order to come up with a delta t, what do we need? What is our link? This is a kinematics problem. So we're going to need a kinematics equation. In order to get there, though, what do we need?
Gravity and what?
Gravity. I don't think we need gravity.
I got V, Vy final, Vy equal minus V times over 2.
G times delta t?
Yeah, thank you, V times over 2.
I don't think that's it.
We're not in free fall. The elevator has tension on it, right?
Yeah, that would be a free fall equation.
Oh, Vf equals Vi plus acceleration times
VF equals VI plus minus. Is it plus or minus?
plus.
No, it's minus.
Minus.
From what I remember.
Acceleration delta t. So
Velocity initial, 1.5. That's 0.
we were told velocity initial.
We'll velocity find that way.
Yeah, velocity final equals 0.
Okay, we know velocity final.
Solve for it, so, no, solve for,
Yeah, but what do I need?
Acceleration, you gotta find acceleration.
I need acceleration. The link between kinematics and force is acceleration. We need the acceleration.
I think we should sleep on it.
I think you have been sleeping on it.
oh, dang.
So how do I find acceleration when I have a bunch of forces?
Force divided by mass.
Yeah, A equals F over M. Okay,
I forgot.
so what is the force here?
Subtract them?
6 or 7.
We subtract them, yes.
50 newtons, right?
We have 750 newtons on the scale as we're coming to a stop. Minus
686.
the actual weight of this guy.
Divided by 71.
And now you know why the mass was given to you, divided by 70 kilograms. What do we get?
But
Oh, the decimal?
Yeah,
0.914286.
0.9142. Okay, meters per second squared. So now we know the acceleration, and that we can plug into our kinematics equation that you told me earlier. So we have, if I subtract V sub I from both sides, I'll have VF minus VI, which would be -5 meters per second squared, divided by A, which would be actually negative A, right?
the time is always constant.
So I have negative 5.0 meters per second squared, meters per second, divided by
I don't really do it.
negative 0.9142 meters per second squared equals delta T. The meters divide out, and then per seconds divided by per second squared leaves us with just seconds on top, so this is going to work. What is our answer?
5.468875.
Okay, 5.469 it sounded like.
Yes, sure.
Now,
So
6, 1, 6, 5.
we can call that 2, so 5.5 seconds. There you go.
It's so long, I think it's because over break, you kind of forgot how to use it.
Yeah, it kind of sounds like it. Okay, so remember your link between forces and kinematics. All right, weightlessness. I've been promising we'd talk about weightlessness for a little bit, and here it is. Weightlessness does not mean no weight. An object that is weightless has no apparent weight. The weight of an object is still mg, it's just that there is no sensation of weight because there's no contact forces acting on the object. An object always has mass, and gravity always exists, even in space, which means mass times gravity is always there, which means an object always has weight. If there's no contact force acting on the object, meaning it's just floating around, then there's no apparent weight. You would feel weightless. That does not mean you don't have weight. If you're free falling, you still have weight. Okay? So, weightlessness, technically, if you don't have any contact forces, can feel weightless, but you still have weight. Okay, and this one, you're bouncing up and down on a trampoline. After you left the trampoline and you're moving upward, your apparent weight is
0. 0.
B. I say B. And you can A, B, and B.
Well, it's definitely not B.
Who said A?
It's definitely not C.
What do you mean it's definitely not D? Why? Because
Why do you say that?
an object that is weightless has no apparent weight. The weight of an object is still mass times gravity. There is no sensation of weight because there are no contact forces acting on the object. So if you're like jumping and there's nothing touching your feet or nothing touching you, no contact forces, it would be, I mean, except for drag, it's, yeah.
You're not hitting the trampoline. Just like in the air.
Yeah, when you're hitting the trampoline, you have a contact
Do you
force.
hate when
Well, when
I
you're-
go
when-
under the- I think. I'm ready to hurt.
But we're talking about when you have left the trampoline, you're not touching anything. So,
Wait, me too.
no, you see,
Well,
you're
not standing
in
on
the
the
air.
That's what
You're
I
in the
thought.
air,
You're in the air.
trampoline.
I thought they got off the trampoline and were like walking on the ground.
Me too, Cole. You're just walking up the hill. Very walking up.
It's D now.
You're bouncing on the trampoline and you've left the trampoline, you're moving up.
Yeah,
D,
force on
it's D.
three is acting.
It's 0.
Is it D?
It's D.
That's
Good
ridiculous.
job, David.
Your apparent weight is 0. You have no contact forces acting on you. Your apparent
So we're
weight,
ignoring air resistance?
your apparent weight is 0. You have no contact
It's a
force.
big heavy object moving it.
Well, how do you know?